that we are trying to build the biggest and the longest bridge in the world. So you can imagine that this is between Calabria and Sicily, where the infrastructure is very bad and the history of construction is extremely difficult. So it is quite interesting that we should try this. And many governments have tried to do this bridge. The idea is originally the Romans thought to they needed a bridge between Calabria and Sicily, and it was never built because, of course, it's not so simple. And in particular, I'm not an expert in everything, so I'm only looking at the possible effect of fretting fatigue. Fretting fatigue in the cables, between the cables and where the cables are lying in the top of the towers. Fretting fatigue is a special type of fatigue when two surfaces are pressed together under high loads, and there are micro slips that cause stress concentration, but also debris and also quite a faster initiation of cracks. So, combination of fretting and fatigue. This topic has never been understood very well. It was the topic of my PhD in Oxford, where they have studied this since 1960s, and I can tell you that the topic is not understood. It leads to a dramatic reduction in metal strength, and it's also one of the most critical challenge in the suspension bridges. So where exactly it occurs in bridges is in the cables, in strength, but also in the anchorages, and in the connections, in the joints, and how you can address this to go straight to the point. You can do protective fillers, lubrication, wrapping in the cables. You can try to do some tricks to do more uniform load transfer. You can do protective coatings, and you can do regular testing, non-destructive testing, to check that there is something, nothing going wrong. Of course, you can also design somehow. You can use codes, and now this is more delicate and difficult to explain. So this was a topic of interest in any bridge. Yes, there were cases where there was a problem of fretting fatigue. Here I show some examples. Okay, so it's not a topic that it's originally only for the Messina Bridge. It's already a history of 150 years. There are many cases where there were broken wires, there were solutions to avoid fretting, and the wires, they showed a 50% reduction in fatigue strength in Japan. So this topic is known in some specialist engineering areas. One of the main and biggest improvement in understanding of fretting fatigue was the MIT crack analog that was suggested by Giannakopoulos and Suresh when more or less at the same time as my PhD they were working with the US Air Force on a topic of fretting fatigue together with Rob Ritchie and Tom Farris and other people in the US. And they suggested a very simple model, suggesting that the contact, apart from details of the geometry and apart from the micro slip, is not very far from a crack. So you can apply fracture mechanics to understand where there is nucleation of cracks and when there is nucleation. And this paper, I think, is the best paper in fretting fatigue ever. And Suresh is not a scientist that we should under-evaluate. And I applied, generalized this model later to consider the details of geometry. So the geometry is not really a crack, but there are like rounded corners. So there is a range of parameters where the contact behaves like a crack, and there is a range of parameters where the contact behaves like a notch. And this model I call crack-like notch analog. Okay, and here you can show some diagrams where I collapsed all the known data of ferritin fatigue. There is of course one parameter, one fitting parameter in this model, which is the ratio is depending on fatigue threshold and fatigue limit. So this is of the order of intrinsic cracks in fatigue. So it's of the order for metals of 100 microns. But except for these parameters, which is a reasonable parameter because we can estimate this from fatigue experiments, the model fits all the data quite well for infinite life. Okay, so in design, we can apply this kind of many different types of approaches. One is to apply knockdown factors, okay? So to consider that ferritin fatigue is more serious than fatigue, but we should also consider that there are scale effects. And so I spoke to Professor Bazant, and he told me that in the case of wires, we should have better behavior for bigger wires than for lower wires. This is very interesting to me because normally the opposite is true. For bigger specimens, you have a weaker strength. So I will be interested to ask him his opinion, which of course I believe. And so in general, we don't. In the past, we didn't design always with the codes. So if we think of the Roman Pantheon in Rome, you know very well that this Pantheon has survived 2,000 years, and it was never designed. There was no stress analysis, no Cauchy, no Navier, no bending theory. And the Romans, they didn't have any model. They had some empirical understanding of cement, which is very interesting and still not understood how exactly they built the structure. If you have better ideas, maybe we can discuss. There is the Brunelleschi dome. Also, it was a very huge progress. Again, there was no real calculation, but it was Brunelleschi who understood how to build the dome in a certain herringbone pattern, and the dome is still there in Florence. So this is the monument of Renaissance, like the Pantheon is the monument of the Roman Empire. There is the Eiffel Tower, which again moving a little bit further, and this is a monument of calculation because Eiffel was a very, very brave engineer, and he applied almost modern methods, and there was some controversy mostly about the aesthetical value of the tower. You know, Maupassant and Flaubert were not very happy about the tower, but if you have been to Paris, you probably know that the tower is still there. So the three examples means that not necessarily we need to design structures, and not necessarily we understand in advance how long the structure will last. But Messina, Strait of Messina crossing was, as I said, proposed many times since the ancient Rome, and it was never built. I don't want to go in details of the proposals. So it is a 3,300 meters bridge in an area where there is a possibility of earthquakes, there is a movement of the plates, and there is strong wind. So it's a real big challenge. And the people have studied this problem for more than 30 years, and there was a lot of funding in Italy, especially in Italy. I don't know why, but it's only concentrated in Italy, this funding, and they addressed many problems. I don't want to say that they didn't care about fatigue. Now, there is a discussion, of course, in the newspapers. There are many contributions from engineers, from geotechnics, and not everybody is convinced that the bridge can be built. They changed also the structure, the solution. Now there are 4 main cables passing over these saddles, and the towers are 400 meters tall, so it's not very easy to do the maintenance also. And So to just have an idea of the dimension of the bridge, here there is a comparison with the Golden Gate. You know, it's a big step forward. So we have, what are these cables? They consist of tens of thousands of parallel aligned high-strength steel wires. Each is individually galvanized, which are air-spun in place from individual wires or using prefabricated bundles of groups of parallel wires. Then this system is called prefabricated parallel wire strengths, PPWS. The final assembly are then compacted into a dense sealed bundle. These cables then support the deck, and the new solution is that they are opened again and they pass over the saddle. It is now, this slide is not correct. It is not true that the fretting fatigue has never been observed. It's contradicted to the other, so there is a mistake, sorry. And there is a committee in Italy who is trying to suggest improvements in the design. They have suggested 67 improvements, and now there is a design that is called the final, but the real executive design will be in 2 years. So they are starting to build the bridge before the final design is approved, which is a little bit interesting. So again, in terms of codes, by the law, we need to stick to the Euro codes. The Euro codes, they have some static rules, and they have also some fatigue rules. They don't really take into account of fretting fatigue because it's too specialistic. For fatigue, they have some special SN curves for every detail, so we can design for this. And these Euro codes, they don't require full-scale testing. If we look at international guidelines like PTI and FIB Bulletin 30, they suggest, this is not by the law, full-scale qualification on the cables with millions of cycles. Of course, we cannot do this on the bridge of Messina. So again, there is a discussion in the newspapers about whether we should do full-scale testing, and again, it's not possible. So we should maybe do some testing of segments of cables, and this has not been done. So all of this should be done in these next 2 years, which is not easy to do, as you can imagine. So the best practices for design that I think I can recommend is the multi-scale testing. So you start from small specimens and you go to near full-size subsystems. You should take conservative margins, applying knockdown factors until testing yields more favorable data. You can improve the contact design, the geometry, the materials, the coatings, the lubrication, that are very important. And you should do in-service monitoring. You can do also redundant systems and independent review. So I think in conclusion, this is one topic that really worries me, the problem of fretting fatigue in the bridge, and requires some further design, and I hope that I will give you some more information in the next 2 years. Thank you.
Thank you.